Okay, so section H.2 is areas and lengths and polar coordinates, and we're going to focus on areas and polar coordinates. And the homework that was due today on section H.2, today, December 9th, I've extended the deadline to tomorrow, Friday, December 10th at 2:55 p.m. Just to give you a little time to work, a little more time to work on that section. Okay, let's see what this is all about. So in figure one, you see a sector of a circle, and you have an angle theta that forms the angle for the sector, and then you have a radius r. So what's the area of the sector of a circle? Well, the area, I don't know if you've seen this formula, the area is equal to 1/2 r squared times theta. How many maybe have seen that formula, maybe back in middle school or high school? All right, well, let me try to motivate it for you a little bit. Okay, so if you just take this off here. Okay, so if you, area of a sector of a circle. Okay, so in section H.2 in the appendix, they give the area as 1/2 r squared times theta. Well, think about this. Okay, I mean this is the formula. Okay, and that's a formula that is it's not hard to prove it, but let's just sort of motivate an example of, hey, this makes sense. Let's say you had the area of a circle. Well, for a circle, to draw a circle, okay, starting from here, if this is your origin and you're drawing a circle, and this is your like starting line, so to speak, and you draw that circle, what's theta equal to for the circle? 2 pi. That's right, Taj, 2 pi. So for a circle, theta equals 2 pi. Now, let's say you wanted the area of the area of a circle, theta equals 2 pi. So, okay, well, then area would equal, for a circle, 1/2 r squared times 2 pi, and that is just pi r squared, right? So everybody knows the area of a circle is pi r squared, and this is just an example of showing you how the formula it works. It works. If you had half the area of a circle, you'd have a 1/2 pi r squared. If you that might make you feel a little more comfortable about that formula. Now, if we go back to the ebook, let's see what we're going to do with this formula. Well, the goal here is in figure 2, you have this function r equals f of theta. So radius is a function of theta. That's a polar equation. And they draw that, and there's a starting angle, theta equals A, and an ending angle, theta equals B, in figure 2 from section H.2. That blue region R, we want to find the area of that region. But how are we going to do it? Well, it's actually an amazing concept, but what we can do is we can take that region and approximate the region with sectors of circles that have different radii. The radii of the region is a function of theta. Okay, so R is a function of theta. So the different points along that polar curve have different radii, and they draw in figure 3. They look at a typical sector. They draw out a radius to the curve. The R equals f of theta sub I. The sector starts at angle theta I minus 1 and ends at theta I, and that's a difference of delta theta is the difference between those two angles. And you know, what we can do is if we divide the polar curve up into these different, if we take different angles, if we select different theta sub I star angles, then we can generate different circle sectors. And if we add up the areas of the circle sectors, we can get an approximation to the area under the curve. That's the idea. And so you see a little piece of area here. Maybe I'll move this up just a little bit. Yeah, a little piece of area is the area of that sector, the ith sector, circle sector, I should say. 1/2 f of theta I star squared times delta theta. Delta theta is the angle that forms that ith circle sector. So what we do is we say, okay, an approximation to the total area of the circle then, I'm sorry, an approximation to the total area of the region would be just the sum of all those all those circle sector areas, the sum of all those I'm sorry, I want to say it right. You have n sectors of a circle, each with different radii. You find the area of each of those sectors and add them, and that will approximate the area under the polar function. That will approximate this area here in figure 2. And so, all right, well, naturally, if we take more and more angles, okay, and add up more and more sectors, areas of the sectors, we're gonna, if we let n go to infinity, if n's the number of sectors we're using, it's going to become an integral. So that's the area of a polar region. That's the area, how we find the area of a polar region. So the area of a polar region where the starting angle is theta equals A and the ending angle is theta equals B, that area is the integral from A to B of 1/2 f of theta squared d theta. And it's a little easier to remember the formula if you just recognize that R equals f of theta. And so now we can find areas of polar regions. Are there any questions before we look at a few examples? Okay. Okay, well let's see here. So one moment here. Yeah, let's look at an example here. Okay, let me give you a moment to copy this example down, and then we'll discuss it. Okay, so what we want to do is we want to find the area of the right half of the region enclosed by this polar curve r equals 4 plus the sine of 4 plus 3 times the sine of theta. So if we were to approach this problem, what's the first thing that we should do? What would you recommend that we do first for this problem? That's right, Tosh. We want to draw a picture. And we can use Desmos to help us draw a picture. We certainly can. Let me see here. So, okay, let me go to Desmos here. I'm going to bring it up. Okay, so here we are. And one moment. Okay, so R equals 4 plus 3 times the sine of theta. Okay, so by default, Desmos uses theta between like 0 and 2 pi. Okay, and this is a cardioid. We call this a cardioid, and we want the area of the right half of that cardioid. So, okay, if we want the right half of the cardioid, then let's see here. Well, we have to figure out what the starting and beginning angles are. Okay, and the right half would be, let me just see if I can maybe make this a little, well, yeah, that's fine. So I think you agree this is the right half. Well, you can see the right half. And, you know, what would this, well, I don't want that. What would this bottom coordinate be? I mean, what would the polar, well, what would the angle be? So what I can do, you see, is I can play around a little bit. I noticed that that bottom point, it's like the where you have a 0 and you go down. That it's not the lowest point, but it's like the little hill, the point that's on the hill. If we look down 90 degrees, we see that point. Okay, if we look down 90 degrees. So you see what I can do is I can, in Desmos, I can change my starting angle to, I can change it to negative pi divided by 2. And the ending angle, I can change it to pi divided by 2. And you see, that gets me the right half. That gets me the right half of this cardioid. That's the area between the vertical axis and the red polar graph, r equals 4 plus 3 sine theta. That's the area I want. So remember, the bottom point, like if you trace out that polar graph counterclockwise, you start where your angle is negative 90 degrees. You're looking down in the negative y-axis direction. That's negative 90 degrees. And when you trace the curve out, when you get done, the top point there between 6 and 8, well, it's 7 actually, right? That has to be when theta is 90 degrees, because 4 plus 3 times the sine of 90 degrees is 7. So notice when you begin at the bottom, when you the starting point of the polar curve, when theta is negative 90 degrees, well, the sine of negative 90 degrees is negative 1. So 4 plus 3 times the sine of negative 90 degrees is 4 plus 3 times negative 1. That gets you a 1, a negative 1. Now hold on. Wait. Yeah, that gets you a positive 1. So what I'm trying to say is this. Maybe I can show it on the whiteboard here. The annotations. What I'm trying to say is this here. You just draw it. Now let me do it better. Desmos will certainly be allowed on the final exam. Oh yes, to help you with these kind of problems. Okay, so this was the origin here. Well, so this starting point here, okay, if you look downward, okay, that starting point the angle is negative pi over 2, and the radius is positive 1. Okay, this is like a positive 1 radius. Now the ending point up here, this is obviously not drawn to scale, okay? Maybe I can make it a little bit better here. Okay, so here, that ending point, you're looking in the direction of 90 degrees with a radius of 7. This distance is a radius of 7. You see? So this is and this of course is r equals 4 plus 3 times the sine of theta. Okay, so it's kind of nice Desmos can help you experiment a little bit. But are there any questions? Are there any questions on this? Here's the area we want. So, okay, so we want that area. Let's now find that area. Let's find that area. So here is solutions, and you notice I say at the top, use Desmos to graph this polar curve. That's fine. It's graphed. And the area is, of course, under the polar graph, goes from A to B, angles theta equals A to theta equals B of 1/2 r squared d theta. And so that's what I have here then. I'm going to let you copy, but please let me know if you have any questions. Okay. So now we just proceed forward and work this out. So the 4 plus 3 times the sine of theta is 4 plus 3 sine of theta times 4 plus 3 sine of theta. And if we FOIL that out, we're going to get the integral where our integrand is, notice, by the way, the 1/2. I brought the 1/2 out here. And we're left with, well, when we FOIL 4 plus 3 sine theta with itself, we'll get 16 plus 24 in sine theta plus 9 squared, 9 sine squared of theta, d theta. And I always find it helpful. I mean, I have here, I have the integral of a sum, but the integral of a sum is the sum of the integrals. And so it's helpful to, I think, split that integral up into 3 parts. Okay, so now we can, a lot of times with these problems where we're finding areas under the polar graph, these integrals can be made easier if we observe symmetries with regards to what we're trying to integrate. So, like for instance, in the first integral is no problem. Second integral, I mean, this is no problem. We can find this second integral easily. But if we notice the sine function goes from negative pi over 2 to pi over 2. And I draw a little picture of the sine function. You notice I have negative area and positive area. And because the sine function is odd, it's an odd function, so those negative and positive areas have to be equal, and so they cancel each other out, giving you the second integral would equal just 0. So you see that just that observation saves me from having to get the antiderivative and work it out. Now the third integral is sine squared theta. Well, sine squared theta is the same as sine of theta squared. Sine of theta squared, well, if I look at a graph of sine of theta squared, that is symmetric about the y-axis. And so I have positive areas in both, of course, but I can write this integral here I can just write that as 2 times the integral from 0 to pi over 2 of sine squared theta d theta. See? So by just observing that the two areas here are that this area and this area are the same, I can just say, well, I want to find this area here and just double it. And so that gets me then 2 times the integral from 0 to pi over 2 of sine squared theta d theta. So it's always nice when we can have like a 0 as one of our limits. It'll make our life easier a lot of times. So are there any questions? Who's feeling good so far? Give me maybe a thumbs up if you're feeling good so far. Okay, Javier's feeling good. And Taj, good. All right. And David, wonderful, wonderful. Well, let's proceed on then to the next page and, finish this problem then. So we go to the next page and so that, I mean, everything should hopefully look okay. Here's where I put in that integral, 2 times the integral from 0 to pi over 2 of sine squared theta d theta. And I have to use a trig identity for sine squared of theta. Sine squared theta is 1/2 times the quantity 1 minus cosine 2 theta. So as you know, you have access to the appendix, and you can find those trig identities as you need them. And now it's just a matter of computing antiderivatives and then putting in your appropriate limits and working out the problem. So it's pretty straightforward. Let me see here. So the pi here, of course, comes from 2 times pi over 2. And the 0 here comes from 2 times 0. And you'll work it out, and you'll get 41 pi over 4 as the answer. And that's what WebAssign's going to want. So for your final exam now, I'm going to want to see this work, this kind of this work, right? Because it's part of the problem, right? you have to be careful with polar coordinates. You have to be just careful with them when you're finding these areas. It's easy to make a mistake, you know. But if you're careful and show your steps, thoroughly show your steps, you should be okay. You notice I use a lot of parentheses and so forth in my work so that I can stay organized. It helps us get the right answer, right? When we're organized, and that's really, I think that's the first step in getting good at math, is just being organized. You have to be organized um, when you do your work. All right, are there any questions before we move to the next example? Okay. Okay, let's look at this example. All right, let me give you a moment to copy this example down. So this is an interesting problem. We want to find the area of the region that lies inside this circle, r equals 3 sine theta, and outside this cardioid, 1 plus sine of theta. Okay, so again, what's the first thing we need to do for this problem? In order to solve this problem, to find this area, what's the first thing we need to do? That's right, Taj. We need to graph it in Desmos. We need to graph this in Desmos. So, okay, well, we can do that. We can do that. So if we go to Desmos here, I've done the graph already. So there, the blue graph or the red graph is the circle, and the blue graph is the cardioid. There it is. And I can make it a little bigger and move it around. So what we would do is now we would take that graph and we would put it on, draw it on our paper, right? And we want to shade in. We want to shade in and notice now I have theta going from 0 to 2 pi as my domains. So I want to, so I can graph the curves, the polar curves. I want to take this picture, graph it, put it on the paper, draw it on the paper, and I want to shade in the region that lies inside that red circle, but outside the blue cardioid. So, okay, no problem. There's a picture. Let me give you a moment to copy that picture down. Let me know if you have any questions. Okay, so you can see the region shaded there, inside the circle but outside the cardioid. And the region starts here at angle theta equals pi over 6 and ends here at angle theta equals 5 pi over 6. But how would you get those angles? Well, those 2 points where the area begins and ends are the points of intersection between the two polar curves. And so we set 3 sine theta equal to 1 plus sine theta. We'll get sine of theta equals a half. Well, sine of theta equals is positive in the first and second quadrants. Okay, so the sine of theta, when it equals a half, we know theta is 30 degrees. So that means theta is going to be 30 degrees, right? 30 degrees, or it'll be 150 degrees. The sine of both of those angles equals a half. But this problem now, we do have the limits we want. We do have the limits of pi over 6 then to 5 pi over 6. But we're going to have to get that shaded area, up there, we're going to have to take that shaded area would be equivalent of taking, this area, which is the area enclosed by the circle from the limits of 30 degrees to 150 degrees, taking that area and subtracting the area of the cardioid that has starting angles 30 degrees and 150 degrees. So you have to get the area, you have to take to get the, I want to say it the right way, to get this area here, you have to take the difference of two areas. And that's what we do. That's what we do. Are there any questions on that? So naturally, 1 plus sine of theta squared, that quantity squared, is 1 plus sine of theta times 1 plus, can't believe I didn't have enough room. Hold on. Hold on, everybody. Rewrite this here. Yeah, so you have 1 plus sine of theta times 1 plus, I'll have to do it this way. All right, let's try it again. 1 plus the sine of theta times 1 plus the sine of theta. And if you FOIL that, you're going to get, what you're going to get here is 1 plus 2 sine of theta plus sine squared of theta. All right, so, and then here, by the way, for 3 sine of theta, that quantity squared, here, you would get 9 sine squared of theta. So that's what we have on the next page. That's what we have on the next page here. And for the first integral isn't going to be a big deal. The second integral, okay, the second integral here, I'm going to write that as the sum of 3 integrals, which I do here. The 1/2, of course, the halves, I factor those out of the integral, and that gets me here. So I want to make my life easy. I want to make my life easy. And believe me, you want to break the problem apart, like I'm showing you. You want to break the problem apart. And what happens, there's something nice here, you see. There are 2 integrals that are like well, let me show you. You have 9/2 times this integral, pi over 6 to 5 pi over 6 of sine squared theta, minus 1/2 times sum of those 3 integrals. But look at this integral here. This is the same integral. So we can combine those 2 integrals. Okay, so if you have 9/2 times an integral minus 1/2 times an integral, that gets you 8/2 times the integral, which is 4 times the integral. So I'm just talking about, that the little, that one integral there. So if we combine those two integrals, we get then the 4/2 times the integral. And we saved ourselves from doing an integral, you see? These are the things you can look for when you do your computations. Okay, these are the things that you can look for. So we have 3 integrals to do. And the limits are from pi/6 to 5/6. The 3 integrals down here, okay, integral 1, 2, and 3. The second integral is not going to be a big deal. But the first and third integrals, we're going to have to evaluate trig functions at pi/6 and 5/6. 5/6 is that can get, I mean, it's fine to work with that, but we might be able to make our lives easier if we examine the symmetry of sine squared and sine of theta from pi/6, which is 30 degrees, to 5/6, which is 150 degrees. Okay, so I have a couple of graphs on the next page that'll be helpful in this regard. Are there any questions before I go to the next page? Okay. All right. Well, so I've graphed here the sine squared of theta and the sine of theta from pi/6 to 5/6. And you can see that about 90 degrees, or pi/2, the graph is symmetric, and so you end up with the same areas. Hold on. You end up with the same areas to the right and the left of pi/2. Same areas. So that means then that we can re-express the integrals as, well, like you see down here. So like for instance, the integral, the first integral from sine squared from pi/6 to 5/6, that's the same as 2 times the integral from pi/6 to pi/2. See that? It's easier having a 90 pi/2 limit than a 5/6 limit. Similarly, the third integral from pi/6 to 5/6 of sine theta d theta can be written as 2 times the integral of pi/6, the integral from pi/6 to pi/2 of sine theta d theta. All right, and so I'm giving you a little time to copy this down, but are there any questions? Are there any questions? See, if you kind of look for this, if you look for these kind of uh, these symmetries, it can help you, because we like angles like 0 degrees, 90 degrees, 180 degrees. You know, those are nice angles to work with, because a lot of times sines, well, you know what I mean, sines and cosines will equal, sometimes it will equal 0 at those values, right? And that makes our life easier. So for the first integral, the integral of sine squared of theta, we're going to have to use an identity to get the antiderivative. Okay, so the identity of sine squared theta is 1/2 times 1 minus cosine of 2 theta. And then now the rest of it, it's basically now just like three little integral problems. If there are no questions, I'll move on to the next page if we're good. I want to make sure I'm pacing myself well. Okay, let's proceed on. Okay, so now, it's just computational. I'm going to let you just copy this, and let me know if you have any questions. I mean, I don't think there's, let me see here. Why is this? Yeah, okay. This actually is helpful. Polar coordinates. I mean, they're used, of course, but it also will help you if you have to take multivariable calculus, which I'm teaching next semester, by the way. In multivariable calculus, you deal with calculus in three-dimensional space, and there are different coordinate systems. Like there's a coordinate system called cylindrical coordinates, and if you understand polar coordinates, that'll help you with cylindrical coordinates. But that's for another day and time, right? Let me see here if there are any questions. Just let me know if you have any questions. So you really have to make use of your organizing symbols. Now, keep in mind, well, yeah, you just have to keep using your organizing symbols here to keep everything straight. And now we just continue the problem. And in the end, we're going to get an area equal, amazingly enough, to pi. That's going to be the answer, because you're going to get a cancellation at this step here. The 2 root 3 over 2 will cancel out with the negative 2 root 3 over 2. and then you know, you get pi. It's really quite beautiful. How many find this kind of pretty cool, these polar coordinates? I mean, uh, yeah, Taj is liking it. It's really very beautiful concept. Ange likes it. Okay. All right. Are there any questions before I stop the recording? Okay.